Okay, hi everyone. Let's get started. So today's session is about sequence modeling. Uh, and to give you a brief kind of rundown of what we'll cover today, we'll be talking about Markov chains, Markov models, which are like the introductory 101 to modeling any sort of sequence, and then moving on to more sophisticated deep learning models like RNNs and LSTMs. Um, we did state on the I did state on the meetup that we'll be covering transformers today. And I realized this is it by itself a quite large combination of breadth and depth for one 1 hour session. So I feel like we'll cover transformers and BERT and all of these uh, like state of the art language modeling frameworks in a later session. So I don't know how many of you attended our first episode or like first version of this, um, but we on last time around we went through a couple of demos and gave like a more high level understanding of what is possible using deep learning in NLP. What are embeddings? What are some classical techniques which are still relevant, and which are the classical techniques which have been replaced? But today's session will be diving deep into what exactly powers these sequence modeling techniques. And as I mentioned specifically, we'll be talking about RNNs and LSTMs. So to give you a brief introduction about myself, I'm a student and a researcher at Columbia University. I've been in this space of machine learning, deep learning for several years now. My father and I started AMLAI back in 2017 with this purpose of, putting together a community where we can discuss state of the art progress made in this field, and even find like applications to Ahmedabad and more generally India. So yeah, let's dive right in and get started. So before before you start off talking about the math and the more complicated things, it makes sense to talk about like why is sequence modeling important? What are some applications which make this an extremely exciting field? And of course, the first application that comes to mind is like the quintessential stock price prediction task. And this is a task that many have tried to master, and many have um, done lots of different approaches. But in recent times, if you look at high frequency trading firms and people who are trading in large volumes, they're running lots of deep learning with sequence models across lots of their own GPUs to be able to get a somewhat better prediction of the market than their competitors. And this is still an unsolved problem. Like if this was a solved problem, uh, you know, uh, we wouldn't be talking about this today. I'd be trying to make money off of this. But this is still an unsolved issue. However, people have tried to make progress in predicting stock price from history. And then, more broadly speaking, all time series forecasting applications. So you can imagine any sort of data set where you have data which is modeled as across time. So let's say you have air passengers over the past 50 years or the past 30 years, month by month, and you want to predict how many air passengers will there be in the next year, or how many people will travel by plane. And in that case, well, you think that okay, it's an increasing graph, right? Over time, people are because of modernization, people are making more money, people are traveling more by air. But then across the graph, then you see the point where COVID hits, and you see the number dropping sharply down. We'll be talking about this as well today. How some models are able to capture not just short-term dependencies, for example, the last couple of months because of COVID, but also long-term dependencies and capture long-term trends. So the more sophisticated the model becomes, the more robust it is to short-term variation. So that's any sort of time series forecasting application where you want to predict the next output in time. And then obviously there's robotics. It's a big field where they're using sequence models to predict position, velocity, and acceleration, given the current types of position, velocity, and acceleration. Self-driving cars. So we'll see like a video of this today. but self-driving cars need not to perceive or percept need not to percept where objects are right now, but they need to predict where they will be in the next half a second, next second, and that will inform the decision they make right now to turn the steering wheel by how many degrees to push the throttle or not. I mean, if you think about it, that's how humans. We make decisions based on where cars and objects will be after half a second or after a second, rather than where they are right now. So that's where sequence prediction is very useful. Speech recognition and speech synthesis. So again, if you think about speech, speech is just a set of observations across time. So let me try to. Okay, we won't be hearing those noises. Okay. Uh, so the same way text is a sequence across time, as we talked about last time, speech is also a sequence of waveforms across time. And sequence modeling approaches are used to convert that speech waveform to text. And then you can apply it in other sequences to go from text to more kind of condensed, granularized insights. Okay, and then of course NLP. Those of you who were there last time, we covered this in extensive detail.
Sequence prediction definition theory.
I'm sorry. I guess okay. Uh, but there are many different tasks which are possible using embeddings, which are generated using sequence models. And to give you a brief overview of what embeddings are just so text are words. Embeddings are numerical representations of those words, which are in like a 300 to 500 dimensional space. And then the last kind of one of my favorite applications, the more kind of exciting one, is music synthesis. So if you train a sequence model on like hundreds of thousands of um, musical pieces composed by a composer, let's say Beethoven, you can now generate music that sounds like Beethoven because your model will now be predicting musical notes instead of text. So those are just some overlying applications which are broadly speaking. These cover broadly speaking all the different things you can do with the sequence model. So how can you classify sequence prediction tasks? Well, there's three main things, right? So you can predict the next value, and this is like the next numerical value. So this would be time series forecasting or sequence-based product recommendations. So today, if you look at a lot of our news feeds are curating content for you. So if you have an app like In Shorts or Google Discover feed, you'll see that at the end of the day, what they use behind the scenes is a sequence model that predicts using your history what you will be most interested in watching next. So that's an interesting application of predicting the next value. Then comes predicting a label. So given a sequence, can you classify this into, for example, sentiment? Is it negative, neutral, or positive? Can you classify this into what sort of text it is? Is it a story? Is it fiction? Is it nonfiction? Like you can classify text into all sorts of things. So even topic classification over a sequence is possible. And then anomaly detection. So I feel like everyone has a smartphone these days, or everyone has worn a Fitbit or some sort of fitness watch. So often, if you look at medical studies which are done using deep learning, they try to use these sequence models to find anomalies in patients' heart signals or brain waves, or even if you think about consumer tech, uh, anomaly detection is used to find anomalies in user behaviors. So that's that's one of the examples of putting a label on a sequence. And we'll see like a very cool use case of this later on. And then the third one is predicting the entire sequence. So given an image, can you predict the entire sequence of words that captions that image? So this screenshot is like part of a project I did, which is a demo that I'll also be covering today. But all you have to do is pass in an image that kicks off the sequence and caption the generator. And today, this has reached state of the art. I mean, this is even beaten humans. So if you think about where the field was 4 or 5 years ago, this was considered at least a decade away, but it's here. And then neural machine translation, so going from English to Gujarati or French to English is also a sequence, predicting a sequence sort of task. And music synthesis, of course, you're predicting an entire sequence of notes. So, okay. Okay. So here's just like kind of a more entertaining example. So here's handwriting recognition. So quick notes. This is the input, like what is actually written by the person on the piece of paper. This is the output, converting those handwritten letters to letters on a computer. And this is actually what the model is taking into consideration at any given time step. So at this position, it's only remembering up to this much. It's forgotten anything that's come before. So this is using a vanilla RNN, recurrent neural network. And there are ways to improve this. There are ways to make sure that at any given time step, the prediction is dependent on all the previous letters, the entire previous sequence. Not all of them are as far back as possible. So why do you need a sequence model to do handwriting recognition, right? Like if I'm sure most of you have seen like the MNIST example where a CNN is used to go from a handwritten number to a number. Like this was first used in the U.S. Postal Office 3 decades ago. So this has been around for a long time. Like why are RNNs important? Well, sure, you can one by one go from a handwritten digit to the digit. However, this doesn't take into account some very important information that we could use, right? We could use what's come before in that sentence to better predict what will come next. So for example, if you see the word Q, okay, if you see the word Q, there's a very high probability. I think it's an almost like 98 to 99% probability that the next letter will be a U, right? So those sort of relationships, like these relationships also apply to words. Like some words are more likely to occur after certain kinds of words. For example, like D is more likely to occur before a noun. So if you see a word, if you see D, then the next word will more likely be a noun. So these sort of things you can capture using a sequence model instead of doing a one by one handwritten letter to digit, a handwritten letter to letter classification. So, and this is an example of music generation using an LSTM. So, if you don't know what an LSTM is, we will be covering that, but this is just fascinating. So this was generated completely from scratch. Like we're not going to listen to the whole thing, but this was generated completely from scratch by a model, which was trained on lots of classical piano music. Okay, so of course, if you're talking about sequence modeling, we'll be starting off with briefly talking about like the 101 of sequence modeling, Markov chains, and then we'll go on to like a use case which I covered last time, but I thought it would also be important to go over it quickly again today for people who might have not attended it or who people want a refresher. And then we'll move on to hidden Markov models, which are kind of the more widely used version of Markov process. What is this complicated thing called a Markov chain? Well, a Markov chain essentially says for a transition for me to go from one state to another, all that depends for that transition is my current state. None of my history decides where I will go next. So if, for example, if you see the word Q, there's a very high probability that the next word next to it will be a U, right? So this is decides where I will go next. this is kind of a very like simplistic example, but these three nodes represent three different states of the market, like a bear market, growing market, bull market. No, I think I got that wrong. Bull market, which is like a growing market, a bear market, which is like a kind of decreasing or falling market, and a stagnant market. So what a Markov chain essentially encodes by definition is that for my next state, if I'm at the bull market, for the for me to decide what my next state will be, all I need is what my current state is. If I know that I'm at the bull market, these probabilities, these transition probabilities will decide where I will go next. None of my previous history will matter. And this seems kind of counterintuitive to the idea of what we've been discussing so far, where to predict the next value, we want to take into account all the history, because that's more robust. But the reason we're covering this is because this is one of the first assumptions people made. It was like, to me, to go to the next state, all I care about is my current state. So this probability um, equation encodes what I just described. The conditional probability of me going to state X, given um, its entire history across time. So n is like the time. So at time n plus one, the probability of me going to state X, the condition on my history, is equal to the probability of me going to state X at n plus one, given the current state. So xn is with xn is the current state. So this is a Markov chain. Very simplistic assumption makes things easy, because now you can just multiply these terms one after the other to get the probability of the sequence. Okay. So let's go through a quick example of a Markov chain, right? So again, I guess I just put the definition here. A Markov chain is a Markov process with discrete time and discrete state space. Makes no sense. And what does that mean, right? So this is just what you'll see online, like, the complicated definitions. But to put it down in like words, the probability of the future is only dependent on the present. Well, yeah, we discussed that, right? And to encode these probabilities, you usually use something called a transition matrix. So on the left, like on the rows, you have all the states. On the columns, you have all the states. And any element Pij inside the matrix is equal to the probability of you going from state I to state J. Okay, so I'm trying to go through this fast, because this is all kind of a refresher. So an application of a Markov chain that has been around for a long time is PageRank, Google's first algorithm to ranking search results. And what they did here was like they constructed a transition matrix that looks like this, to go from one web page to another based on these rules. And I won't go into these rules in detail, and I'll share these slides for those who are interested. But once we have this transition matrix, you can now use what's called the PageRank algorithm to predict what are the most popular web pages that you want to recommend to a user. And all of this is possible using this one very simplistic Markov chain assumption. So, okay, I also don't want to go into detail here, but essentially this is a saying, if this was my this is my initial distribution. So let's say I had 4 web pages. I want to rank 4 web pages. Initially, assume all 4 of them are equally likely. So it's 1 by 4, 1 by 4, 1 by 4, 1 by 4. I'll keep multiplying this by this transition matrix until I converge to a stationary distribution. When I rank the final result, that will be, when I sort the final result, that will be my that will be my ranked list that I want to recommend to a user. And there are ways to do this more optimally, right? So instead of multiplying this matrix like n number of times before it finally converges, you can actually use some clever linear algebra to find a stationary distribution and do this in one step. But again, let's not get into this in detail. I just wanted to cover this to show like Markov chains are actually useful. They're not just this old simplistic assumption that people have made up. And then like another example is you can rank sports teams. You can rank cricket teams by constructing this transition matrix this following way, and then using this PageRank algorithm. And then you can, given last year's IPL results, get a prediction of what the next year's MPL results will be. This is also an application of PageRank. Then you have text rank, which is essentially you're using Markov chains to you're using the Markov chain assumption to summarize text, and you should construct a transition matrix using a similarity between two sentences. And the intuition here is we want the summary. So if you have 100 sentences in the document, you want to boil it down to 10 sentences. We want the 10 sentences inside this document to be as similar to as many sentences as possible in the entire document. Because then that means that those 10 sentences will cohesively summarize the entire document. And so I also went through a demo last time. You can check this out here. But again, this was just one of the initial algorithms people came up with to summarize documents. But now this has reached an entirely different level because of deep learning. Okay, so what are hidden Markov models, right? So hidden Markov models combine this assumption of Markov chains that my future is only dependent on the present, along with something called an emission. So what you have here are all of these are hidden states. These are all nodes, and each of these hidden states can correspond to emissions. So in this particular use case, we're talking about the weather. Rainy and sunny are the two hidden states. So what these probabilities mean between rainy and sunny is that if today is rainy, the probability of tomorrow being sunny is 0.3. The probability of it staying rainy is 0.7. And if it's sunny, the probability of it being rainy tomorrow is 0.4, and it staying 7 is 0.6. So you have this Markov chain assumption encoded as the same assumption that we talked about earlier. But now you also have this emission probability. So then each state can have multiple emissions, right? So for example, in this case, the emission is like, what will I decide to do today? Will I walk? Will I shop? Or will I clean? So these are, if it's rainy, the probability of me cleaning is 0.5. The probability of me shopping is 0.4, and the probability of me walking is 0.1. You can notice all of these three sum to 1. So this essentially enables you to do things where you have, so one application we discussed last time is POS tagging, right? It's a part of speech tagging. So you have a bunch of words in a sentence, and you want to, for each word, assign, is this a noun? Is this an adjective? Is this an adverb? And so on and so forth. So for something like this, you use a hidden Markov model where each hidden state is the word and each emission is the actual POS tag. Then you use this complicated looking formula, but it's really essentially saying that the probability of my sequence of hidden states along with the emissions, X and Y. So X is the sequence of hidden states and Y is the sequence of emissions, is equal to the product of all these transition probabilities, as we saw in the matrix, multiplied with the probability of these emissions. So in this case, if I were to say, what is the probability of this following sequence, right? So I'm giving you an example. Let's say the sequence is, today it's rainy and I shop, tomorrow it's sunny and I clean. So what is the probability of that sequence? Well, that's equal to probability of rainy given starts, that's 0.6, multiplied with the probability of sunny given rainy, that's 0.3. That encodes the hidden states. And multiplied by the emission probability. So multiplied by the probability of me shopping given rainy, so multiplied by 0.4, and multiplied by the probability of me, well, I said clean, right? So probability of me cleaning given sunny, it's 0.1. So that will be something around like 0.00 something. That's the probability of that sequence. This is like one of the initial sequence models that came up, and a lot of what came after this is based off of this hidden Markov model. Okay, moving on to the more kind of fun or more state of the art stuff. So these are recurrent neural networks, right? And recurrent neural networks essentially are a sequence of linear algebra operations. So essentially, what I'm saying is I have a bunch of input observations represented by my input vector xt. I keep track of something called the hidden state, which is just a matrix. And I will output for each corresponding time step, I'll output whatever I decide the prediction is. And this is a boiled down version of talking about this, right? So ht, the hidden state, is equal to some function, which is a function of the old state. So think about this. This is the Markov assumption we saw earlier. My current hidden state is only dependent on the last state and the input vector at this current time step. So let's kind of formalize this, right? So what is this update equation, right? So this fw function is essentially, I'm going to multiply my old hidden state vector ht minus 1 by this some matrix whh. This matrix is learned over time. I'll add to this my input at that state multiplied by some matrix wxh, which is also learned over time. And then I'll do a tan h. Tan h is just a function that boils this down to something between -1 and 1. So let's unroll this, right? When you unroll this, think of these x's as words, right? So you have words across the sequence. You have these matrices wxh, which are constant across the sequence, and this matrix whh, which is constant across the sequence. Both of these matrices are learned over time as per the training process. And then you have this, by the way, you also have another matrix why, which decides the output at every time step. So given this hidden state, I'll multiply this hidden state by a matrix why, which is learned, to get the output at that time step. Okay. And then if you know the concept of loss, well, a loss is essentially, I'm going to compute the loss between the ground truth and my prediction, and then I'm going to add all of this up to get an overall loss. And then you'll back propagate this loss across the sequence to find the right values of why, wxh, and wyh. wxh, whh, and these three. I might have gotten those wrong. whh, wxh, and why. So, if that doesn't make sense yet, that's okay, because we'll go over back propagation of that mathy stuff a couple of slides down. Before that, I want to give you an intuition of why this is important. So here's a kind of interesting example where we take in, so this is an application of an RNN working real time on a self-driving car. So we'll take in a sequence of images, essentially a video, and all of these images are also labeled by the object velocities. So if you look at a self-driving car, you'll notice there's this big box, cylindrical type sensor on the top called the LiDAR. So these cars usually have both a radar and a LiDAR, which enable them to find the velocity of moving objects very accurately. So these images are also labeled by the velocity of each object. And the RNN will predict the time to collision of the car and all of these objects, the future position of these objects after half a second, the future velocity of these objects after half a second. And the more interesting objects are cars and pedestrians, right? Buildings don't move, so these models aren't applied to those sorts of objects. Let's take a look at it.
Today's drive mission is about predicting the future, specifically predicting the future position and velocity of dynamic obstacles on the scene, such as cars and pedestrians, using recurrent neural networks. In this clip, the white boxes represent current object positions, while the yellow boxes are the recurrent neural network's predictions on where these objects will be about half a second in the future. And to simplify visualization, predictions are refreshed every half second. We can see that as time passes, the white boxes move towards the yellow ones in 2D image space, which shows that the network is correctly predicting future object motion. And this information would help the car to anticipate and adjust its trajectory as needed. Here, the network is predicting time to collision information, or TTC, between the ego car and objects on the scene. The red boxes represent cars that are getting closer to us and would have lower TTC, or equivalently higher urgency, to avoid a collision, while the white boxes represent cars that are moving forward at about the same speed as us. The green boxes represent those that are moving further away. And the number at the top of each box represents the computed urgency, which mathematically is the inverse of the time to collision. And here we see the same computation performed for a scene with pedestrians. And that was Drive Mission 32, which we affectionately refer to around here as Project Back to the Future.
Great. Okay, so that was by NVIDIA. And like self-driving cars are one of the most exciting applications of sequence models, because knowing where an object is in the future, like half a second later or a second later, is extremely important in deciding what my actions will be at right now, at the current time. Okay. All right. So how are these weight matrices learned, right? WHY, WH, and WXH, like these aren't like not magic. You can't magically come up with these matrices and hope that you will get the right output and the updates will be correct, and you will be inputting the right proportion of the input using this matrix, right? So these matrices are learned over time. And what that essentially means, like learned over time, is given many of these sequences, you'll always be computing this loss, aggregating this loss to L, and taking the differential of L with each of these weight matrices and sending it back across time. And the way this is learned is using like the chain rule. And so you can imagine one issue with this is if you're gonna multiply, if you want to find the differential of, like, let's say L3, the loss of the last time step with respect to, let's say, X0, the input, the original input, you'll have to multiply a lot of different differentials with respect to WHH and WXH, and the number of such multiplications will be equal to the length of the sequence. So for something which is four units long, this is not an issue. RNNs are capable of doing this. But for a sequence which is like 20, 25, like if for a sequence that's that long, these multiplications very easily die out. If you multiply a small number again and again and again, it vanishes to zero. And that's called the vanishing gradient problem. So that is the motivation behind LSTMs. The issue with RNNs is the fact that these RNNs are not able to encode long-range dependencies. For a current time step, it is not able to take into consideration what it saw 15, 20 time steps ago. And this, in many cases, is very important. You want to be able to take into account a large portion of the history and not just a recent portion of history. And a good example of where this is relevant is, for example, let's say you're doing question answering, right? So you have this paragraph and you run an NLP model that essentially is meant to answer a question. So you ask, and the paragraph is like this, right? So the paragraph says, my name is Jaidev. Then I have a bunch of things about myself, which are kind of tangential, like where I go to school, what is my hobby, all of that. And at the end, to my NLP model, I'm like, okay, question, what is my name? So if the NLP model only has a representation, which is created using an RNN, and this is a long document, it will not be able to, it will not have encoded the fact that my name is Jaidev, because that's, that it saw that a long time ago, like a couple sentences before. But if you use an LSTM, it is able to forget parts of that paragraph which is not relevant to this task of question answering and only focus on parts which are. So it'll be able to encode the fact that my name is Jaidev, which is like a kind of a long-range dependency. So this is why LSTMs are important. Encoding long-range dependencies. RNNs, so to summarize, RNNs suffer from short-term memory. They're only able to take into consideration the very recent history when doing the updates to the hidden state and giving us a prediction. So for long sequences, RNNs are not able to carry information from earlier time steps to the current time step. And as I discussed, on trying to perform tasks like machine translation or question answering, just using a vanilla RNN will leave out important information you saw earlier on. So you want to use an LSTM. And LSTM, by the way, stands for long short-term memory networks. The reason it's named this like oxymoronic name is because it encodes both short-term memory as well as long-term memory. Sorry, long short-term memory networks. And as I discussed, this is important. Why? LSTMs are important. Why? Because RNNs suffer from vanishing gradients. So when you're training them, those repetitive multiplications using the chain rule, those gradients go to zero. So you need some more clever tricks, and we'll discuss some of those tricks very briefly. And what this means is like extremely small gradients do not contribute to learning. So to update my weight matrix at some time t, if I'm gonna take the derivative of the loss at that time step with respect to an input I saw a long time ago, that value, that derivative will be close to zero and will not be contributing to my update equation to the current timestamp. So to fix this, LSTMs emerged. They didn't emerge, someone invented them, but like they were bound to emerge. Lots of people were working on solving this issue of short-term memory. So the key behind LSTMs is if you keep, along with the hidden state, we also keep something called the cell state. And the cell state here is kind of like this horizontal line that goes across time. So these aren't really changed much. It's like, an analogy used in this particular blog post, which I would recommend reading if you want to go more into the math, is it's like a conveyor belt. Information can pass across this straight line called the cell state very easily across a long sequence of units. So, so this is one addition, right? So this is one value add on RNNs. And along with the hidden state, we also have the cell state. But at the same time, we also need a couple of different strategies to be able to update the cell state and the hidden state. And there are different gates that are used, right? So there's something called the input gate, the cell state update gate, forget gate, and output gate. So the forget gate, for example, essentially tries to forget parts of the previous sequence which are not important, and only keeps the crux of the sequence. The output gate is used to get the prediction. The input gate is used to decide what parts of the input am I gonna be taking into consideration when I update my cell state. And the cell state is essentially used to update this CT, this straight line from one unit to the next unit. But this is kept as relatively unchanged as possible. So I guess, like, if this doesn't make sense, here's a better way to put it, right? So the intuition in LSTMs is that we only retain information which is very relevant to my task. So if my task is making predictions, I will only take into account, or my LSTMs will only remember things which matter. And how does it learn to decide which things matter? It learns this because when you train this over many, many sequences, these weight matrices arrive at the right value, which is needed. So for example, if I'm training an LSTM to predict the sentiment of a review, given this paragraph, these weight matrices will be tuned over time to only take into account stuff like amazing, perfectly balanced breakfast, will be buying again. Because it knows these were important when it was trained. It knows that these were important in deciding what the output classification was. In this case, it's a positive review, right? So this will be a +1. It's like +1 is positive, 0 is neutral, -1 is negative. If you did this using an LSTM, well, an LSTM will only be able to take into account the last couple words. In this case, it might not be an issue, but if the last couple words are kind of just neutral words, it won't be able to take into consideration the fact that it's amazing and perfectly balanced breakfast a couple sentences ago. So another use case of LSTMs for sentence embeddings. So generally, if you look at how people did sentence embeddings and how even many people do today, is called continuous bag of words. And continuous bag of words is essentially a way of saying that I'm going to disregard any ordering of words in a sentence. So for example, if I have study hard, don't play, I don't care what order I saw these words in. All I will do is take the individual word embeddings. Word embeddings are like the word vector representations, just a sequence of numbers that represent a word. So I'll take the word embedding for study, the word embedding for hard, don't play. I'll just average them up or I'll sum them up. Doesn't matter. Now that will represent my sentence. And this seems kind of like, kind of a stupid thing to do, right? It's like even in this example, you can see that, the order of words are extremely important. Study hard, don't play is completely different from play hard, don't study. However, even though this seems like a very trivial, naive way of doing this, continuous bag of words have worked well enough in practice when you're trying to come up with sentence embeddings. But this is before LSTMs. When LSTMs came into the picture, people realized that these can be used to get very nice sentence embeddings, which are specific to the task I want to perform. So in this case, our task, for example, is machine translation. I want to go from India is a beautiful country to the Hindi version of that sentence. Bharat ek khoobsurat desh hai. So what we'll use here is something called an encoder-decoder architecture. As I discussed before, over time we're propagating this hidden state. So this hidden state is getting updated as it sees these new words, as it sees India, as it sees is beautiful country. At the end, after a country, this hidden state has been updated to a vector that currently represents the entire sequence of words before it. And then this hidden state at the end is plugged in into another LSTM or another RNN, which is used to decode this hidden state into the Hindi version of the sentence. And these are trained jointly usually. So what happens is you pass in India is a beautiful country, you get Bharat ek khoobsurat desh hai, then you compute the loss between this and this. And this is usually done using like human labels. This has been labeled before by humans. And when you compute the loss, this is trained jointly to both improve the quality of decoding the hidden state to Hindi, but also at the same time improving the quality of the hidden representation itself. So what happens is you can actually use this HT at the end of India is a beautiful country as a sentence embedding. So I just described all of what I wrote here. Essentially, once you've minimized the joint loss, you can get rid of this. You can discard this decoder, and this is your LSTM encoder. You pass in any sentence, it gives you a sentence embedding, which will be the hidden state at the last word. So here's a quick demo for text classification. So I'm gonna, all right, so I'm running these demos on a different laptop. So what I'll do is I'll do all the demos at the end actually. No, because then I'll have to shift accounts. So I'll do this demo as well at the end. But a quick note here before I jump to the next slide is that there are many different ways you can think of sequence models. Like one is one-to-many. So for example, an image to many words that represent the caption, many to one. So in this case, text classification is many to one. You have this entire piece of text, a paragraph, and you're classifying it into positive or negative. Or maybe any sort of class label you want it to be. You can go many to many, like this decoder is this encoder decoder architecture is many to many. You have many words, which is the input sentence, and you have the output sentence, which is also many words. And then you have many to many. So this, for example, is across time, I have sensor readings. I want to go from sensor readings to some sort of prediction, like I want to go from, let's say, waveform to word, but you'll need like another CNN or something here, but I want to go from a waveform to a word across a sequence, right? So I'm speaking something every single time, real time, Siri or Google speech to text is going from my waveform to the word, waveform to the word, waveform to the word. So that's many to many. That's a good example. Okay, so here's another very nice example of how you can use an RNN on sensor data. So instead of speech signals or text or stock prices, we have raw sensor data. In this case, the sensor data comprises of data collected from the gyroscope and the accelerometer based on anyone's smartphone. So if you look at your smartphone today, it has this gyroscope which tells you the orientation. It's used when you play these games like Need for Speed and all of these. And you have an accelerometer which is a sensor on your smartphone that tells it what the acceleration is in X, Y, and Z. So everyone's smartphone has this. So what these guys did were they put the smartphone on this pouch and made this guy walk and do all sorts of tasks. And they recorded the sensor reading simultaneously. So lying down, walking, when you go down a flight of stairs, up a flight of stairs. These are all different activities. And you can see how the sensor readings are changing as he does these. So what they did was they compiled this huge data set. So this is data set called the human activity recognition data set that has essentially on the rows, it has these sensor readings and across a sequence, I guess, of like, I don't know, 5 seconds, 10 seconds, whatever they keep it to be. And they also have the correct label of what the human was doing when those sensor readings were recorded. Was he walking? Was he walking upstairs, sitting, standing, and laying? And then they use an RNN to, given these sequence of signals, predict one of these classes. So essentially, this is a classification task. It's not different from from text classification. Instead of text, you have signal waveforms, and then at the end, at the very last time step, you're predicting one value, which is the class label of these activities. So probably like 1 to 6. You'll get a prediction that goes from 1 to 6. Um, that corresponds to these 6 activities. So another great example is image capturing, right? So you have this input image. Let me just check the time. Okay. You have this input image. Use a CNN to convert this into a sequence of numbers, a vector of numbers called the feature vector of this image. And then you'll pass this into an LSTM. And what this LSTM will do is, given this initial input, it'll take the, always predict the word start, take the output at this time step, pass it back into the next time step as the input, update use this input and the weight matrix WHH to update the hidden state, get an output, pass this output back in, use the input matrix WXH to and the previous hidden state to get this time steps hidden state. I can call it HT. HT is the hidden state at this time, and HT is equal to tan H WXH multiplied by the embedding for giraffes plus WHH multiplied by the HT minus 1 hidden state. So if you don't remember all this, that's fine. Like these are all just naming conventions you can look into. But the point is, at every single time step, this update equation gives you the next hidden state, which is used to give you, which is multiplied by WYH to get the output, and this is passed back in. So essentially, you kick this off with this input image, and then you pass in the output at every time into the next time step. The giraffes goes in, standing goes in, and at the end, you'll predict the word end, and that will be the end of the caption. And I actually did this for one of my class projects, and I'll walk you through it kind of code cell by code cell, not line by line, but what each individual cell in the Jupyter notebook is doing. And so yeah, let's actually go to that right now. So. Oh, and quick note, when I was describing this, I was describing this from the perspective of an RNN, where there are just like 3 weight matrices. But keep in mind, like LSTMs are just kind of advanced versions of RNNs. What they're doing here is also a combination of forget gates and cell state update gates, a little bit more complicated things, but the intuition is the same thing as an RNN. The updates that occur here depend on the previous hidden states and the current input. Okay, so This is just kind of pre-processing stuff. I use the ImageNet data set. Converting that into, so these are essentially just pixels, right? We're viewing that image as these sort of pixels between 0 and 255. So they're just some images. Importing the Inception V3 CNN model. This will convert our set of pixels, matrices of pixels, to numbers. But these numbers, this vector can now be plugged in as a feature vector to kind of more downstream tasks. This is just a summary of the CNN. We're not talking about this today. We're talking about RNNs. We can ignore this. It's a pretty long, pretty deep model. Okay, what we'll do is what we'll say is our image encoding, the feature vector, is equal to the output at the very last layer. This just gives me this, for an image, this gives me a vector that represents that image's features. I'm just running a generator here. Okay, now I have this, I now have a data set that goes from Inception V3, ImageNet image, the corresponding caption, and some human has done this labeling and come up with this data set. So this reads that data set. This is an example of what an entry in the data set looks like. This is the image from ImageNet. This is the corresponding caption, the boy laying face down on a skateboard being pushed by a different boy. So now, this is just again pre-processing stuff, or more like bookkeeping stuff. And here comes LSTM. So as we discussed earlier, we pass in the start token along with the Inception V3 feature vector of that image. And the output at every timestamp is passed back in as input to the next timestamp. So if I pass in start and the image, I get a dog, beach, so on and so forth. This is like imagine this is before it got trained. This is a bad example. But over time, these weight matrices, these update matrices are learned and they become better. So this is again bookkeeping stuff. This is the decoder. The decoder here is the LSTM. So as I talked about earlier, there's in the encoder-decoder architecture, the decoder goes from representation to the output sequence. In this case, our decoder is an LSTM that goes from the representation, which is the Inception V3 image vector, to the output sequence, which is the caption. Let's shut that off. Okay. So this is what the decoder looks like. You have an input layer, dense layers, an embedding layer, bidirectional layer. Bidirectional essentially says I'll do this, forward pass for prediction, backward pass for back propagation in both directions, not just left to right, but also right to left. So if I have a sentence like, my name is Jaidev and I like snowboarding, it'll do this forward prediction pass from my to snowboarding, but it'll also do it from snowboarding to my. And this is just like a clever trick to improve the accuracy, not necessary at all. So now I define this decoder, this LSTM, and I will train it together with my data set, the data set of image to caption. And yeah, these are a few examples. A man in a blue shirt and a black shirt, This is not that good right now. But then you use something called an image beam So here's like a better example, right? A boy in a blue shirt is jumping into the water. So now, like a trick here is like, instead of choosing the most probable word when you're coming up with the output at a certain time step, you sample you sample from it. You sample from the different words that could come up. And that improves accuracy. Or that improves the captions. For example, this is like a black and white dog is running with a ball in its mouth. It's like near perfect. And this is actually something which you can do on Colab in a couple of days. So imagine the level at which companies like Facebook and Google are using image captioning for their own services. It's a lot more sophisticated, but the core of it is the same. Okay. So yeah, that was the last slide. But the reason, the one thing we missed is like this particular demo. So I'll switch participants. This laptop. So what I'll have to do is make myself the host. So here's so bear with me for a second. There it is. One time, that's fine. So here's an example where we're classifying text with an RNN. We're doing sentiment classification. So on the IMDb movie review data set. So you have movie reviews and the corresponding label. This is a positive review, negative review, so on. So first we'll create the model using Keras. This is training the model. I feel like IMDb is just one of the inbuilt data sets you can just import. Yeah, so it's an inbuilt data set in TensorFlow you can just import and use. It makes things easy. And here's an example where we're predicting the sample text. So the movie was cool, the animation, the graphics were out of this world. I would recommend this movie. Gets a 0.27, which is positive. And if you do it with padding, you get 0.3, which is like a boost in accuracy. But then if you use an LSTM, you get better. You get the exact you get much better predictions, right? So for example, the movie was not good. The animation, the graphics were terrible. I would never recommend this movie. It's -3, which is very negative. And then if I just change the words around here, actually, when I ran this, I changed this to great. Change this to fantastic. I would recommend this movie. Now the LSTM recognizes this is in a very positive review. And the reason the RNN failed was because RNN was only taking into account, or only could take into account the last couple words. And LSTM was able to encode everything, all the history that came before it. So even the fact that the movie was great and the adjective fantastic, all of this were picked out by the LSTM into its representation. So yeah, that's an example of using text classification for RNNs. Yeah, an example of using LSTMs in RNNs for text classification. The first half was using a vanilla RNN, the second half was using an LSTM. But again, this time was also on the slides. This is, by the way, a demo by Google Research. I just found it today morning, but it's a very nice example of doing sentiment classification on reviews. Okay, yeah, that's pretty much it. Stop sharing. Okay. I guess we only have 2 people watching this on Zoom. Maybe there's more on the YouTube live stream. But uh, does anyone have any questions? Maybe suggestions for maybe something you'd like to see next time. If not, you can just always like leave leave a comment on the meetup. I'll take I'll look at that. But yeah, if not, well, thank you for attending and thank you for sticking through it. And yeah, see you guys next time.